Okay, and before we get started into the physics, I just wanted to alert you to a couple of announcements on Canvas. So homework is online. Most people, I think, have already enrolled. Please do that if you haven't. The first homework is a little lengthy, but hopefully not too bad. Let me know if it's taking like an obscenely long amount of time. Pearson gives you estimates as an instructor, and they said 3 hours, 4 hours. Which I know is long for homework, but it's also supposed to be an accelerated course. So this is kind of like 2 homeworks together. And then, we're trying to, I tried to spread out the material so that you're not just front loading all of the fluid stuff. But anyways, let me know if you have any questions about that. Feel free to email me. And then hopefully you've met with the group members in your group project. But if you're having trouble reaching them, again, reach out to me or to one of the TAs and we can help you get in contact. Yeah. The group member, like the spreadsheet. Yeah. So it should be in the group project PDF. Does that link not work anymore? Okay. I'll make it put in an announcement because I know it is a little hard to find, but it's in the PDF describing all the topics and like how the group project works. I probably should have highlighted it or something to make it a little bit more noticeable. Okay, good. So we're going to hop back into our introduction to thermodynamics. So last time we were talking about thermal expansion, which is this idea that for most materials, when you heat them up, they get bigger, and when you cool them off, they get smaller. And it's a pretty small effect, like as we saw in our example last time. If you have this, 2-foot wide shelf, it's going to shrink by a few millimeters when you cool it down to liquid nitrogen levels. But because the way that thermal expansion and contraction works is that it's a fraction of the total length. If you have a really large object, that fraction of the length can get to be quite big. So especially when you're talking about buildings or bridges or that sort of thing, you can have enough change in size that maybe the way that you connect 2 objects like screws and bolts, those things can be put under immense stress because typically there's not much room for them to adjust themselves. So it's an important property to keep in mind. I want to give you a notable exception or a partial exception, which is one of the most common molecules on the planet, water. So water has some really weird properties. This isn't the first or the last of them, I think, that we'll discuss. But one of the weird properties of water is that it's actually less dense in its solid state. And that below a certain temperature, which is 4 degrees Celsius, water doesn't undergo typical thermal expansion. It actually undergoes thermal contraction. So we have a nice graph of this. So first off, let's look at the graph on the left. And this is a great reading exercise because I want you to look at the units. So the x-axis units are very similar. They're the same spacing for both of these plots. Just the one on the right goes into the negative a little bit so that you can see the behavior of ice. But the y-axis units are wildly different. Okay, so the y-axis units on the left are changing by parts per 1,000, whereas the y-axis units on the right are changing by 1/2. Each time, so a significant difference. And so this U-shaped curve, oh, I forgot to set up my little tablet. 1 second. There we go. So this U-shaped curve, if you look at the part to the right of this dip, that is a graph showing thermal expansion. You can see how this is roughly a straight line. And, this is following this same formula, alpha delta T gives you the fractional length change. So there's some slope to this alpha, and then the x-axis is delta T. And so that gives you a linear relationship. And, it's not exactly linear. When I erase this, you can kind of see that there's a bit of a slope to it. But once you get past, I don't know, 7 degrees Celsius, this quadratic really flattens out and is well approximated by a linear relationship. However, this minima, or this minimum point, is really weird. And so I think it's always, as we go through this thermo section, we're going to always be asking ourselves, we know things are made of atoms and molecules. So what's happening? When these ideas were first discovered, people had no idea what materials were made of. And so all of these were just empirical relationships, things they measured about the world. But now we can actually talk about some sort of an explanation for a lot of the phenomena that we'll discuss. And so with water, we know, or a lot of us from chemistry know, that the thing that makes water weird is that it's just very polar, right? Water molecules have a positively charged end where the hydrogen is at, and a negatively charged end where the oxygen is at. And because of this, they attract each other, they stick together. And this 4 degrees Celsius point is basically the temperature where you've cooled it down enough that these bonds have really started to form throughout the water, these polar bonds. And so I'm just going to draw water molecules like this. It turns out, and we'll discuss this more on Thursday, that when things are, held at some temperature that's not absolute zero, they're bouncing around, they're colliding. And those collisions bring the molecules really close together. Okay, and so the average molecule spacing for water when it's a little warm is going to be, held slightly closer together. But once it begins to get colder, which is this region to the left here, more and more of these polar bonds begin to form. And the bond length, the separation between molecules, once these bonds have formed, is actually bigger than the minimum or the average distance during the molecular collisions. And so this explains why we get this curve back up. As we cool down, we form more and more bonds, and the water gets bigger and bigger. And then at a certain point, we get this very dramatic, phase change, which is where the water goes from a liquid to a solid. And at that point, all the bonds form throughout the structure, and it just causes the molecules to really spread out. And this is why, if you're from a colder region, you probably know that, the roads look really crappy when springtime comes, because in fall, liquid water seeps into cracks. And then as it freezes, it expands and makes new potholes and cracks wider. And then it melts away in the spring. And so it's a very similar idea to this. But anyway, so that's all I wanted to say here, is that, first of all, you should know this important property of water. You may be quizzed on it. And you should know that liquid water has a higher density than solid water, which is critical to life. Life began in the water, and you can't have aquatic life if water sinks when it freezes, because then it would just get piled under ice, or it would be a lot more difficult at least to sustain. But then it's also a good exercise, like I said, in reading graphs. There may be some homework problems similar to this, where you'll have different seemingly contradicting plots that are actually just the same, but have wildly different units. Okay, so moving on from that, specific heat, or your book calls it specific heat. The better name is specific heat capacity, is a property of materials that gives us a way to finally relate heat and temperature. So this was something I emphasized last week, that heat and temperature are different, right? So heat is an amount of energy that you're giving something based on a difference in temperatures. So if I start a fire and I stand next to it, the fire is giving me heat. This is a bit sloppy language. If you want more detail on the correct language, you can check the book. But heat is an energy given from one thing to another based on a difference in temperature. It's very similar to work, which is an energy given from one thing to another based on motion. Okay. And if you remember from last week, the first law of thermodynamics is that the change in energy in something, which is related to its temperature, is connected to the work done plus the heat done on the object. So I can raise the internal energy of something like a gas by compressing it, or I can raise the internal energy by starting a fire and warming it up because there's a difference in temperature between the fire and the gas. Okay, but for the moment, we're more focused on this heat part of the equation. And so an important idea is, how do we connect the heat to temperature? And it turns out to be material specific. So different materials will have different temperatures for the same amount of energy given to them. And so again, thinking back to, we know materials are made out of atoms and molecules. So how could this be? So different structures, different molecular structures are better able to vibrate, basically, or to somehow, in the case of metal, it can be less about the vibrations of the nucleus and more about the transmission and vibration of the electrons that are kind of free to travel in the metal. So some particle, whether it be the whole atoms jiggling or just the electrons that are more freely movable jiggling, allows for the conversion from some temperature difference into a amount of energy in the substance. Okay, and so the formula which is often known as the MCAP formula, is that Q is MC delta T. And remember from last week that we have two temperature scales in the metric system, Celsius and Kelvin, but it doesn't matter which one you use if you have delta T's in your equation. So this is another equation where you can use Celsius, you can use Kelvin, it's fine either way. So we just care about changes. But when we get to the ideal gas law, we want to use Kelvin because it just has, that's PV equals nRT, there's no delta T. So the absolute amount of temperature is important in that case. Okay, so what does this tell us? Well, it tells us, apparently it thinks I'm not logged in. Okay, well, only have black today. Anyways, it tells us that if you have a more massive object, so a bigger object, that it takes more heat in that case in order to change its temperature, which hopefully makes sense. So, if you have a larger animal like an elephant compared to a smaller animal like a mouse, if they both stand out in the sun, the mouse's temperature can change quite a bit, whereas the elephant's temperature is going to be much more stable. So hopefully that feels straightforward. And then the C is this material property, which is the specific heat capacity. Okay, the word specific there just means that we've divided out the mass. So, my phone has a heat capacity, but the plastic making the case, per kilogram has a specific heat capacity. So sometimes I'll accidentally just say heat capacity for a specific heat capacity, hopefully not too confusing, but most people in engineering and physics are very sloppy about calling specific heat capacity specific. It's just kind of assumed. But there are two types of specific heat capacity. So there's a mass-based specific heat capacity, and there's a molar specific heat capacity. So this is a mass divided by mass, and this is divided by your number of moles. So for gases, we tend to want to use the molar heat capacity, whereas for solids, it could be either or depending on your situation. In physics, we tend to use the mass-based one. Chemists love moles, so you'll see that more often in your chemistry classes. And what you can kind of start to see from this chart is that the heat capacities for different objects, it doesn't, state of matter doesn't tell you very much about heat capacity. There are liquids with bigger or smaller heat capacities than solids. And as we'll see with gases, a lot of the time, the heat capacity of gases can be pretty similar to these as well. it can kind of be exaggerated when you start to look at the mass scale, because gases are so low in mass that it looks like they have extremely large heat capacities. But if you look at the molar heat capacities, you can more easily compare them, and you'll find that they're very similar. And I want to mention here that, we all know most materials can transition from gas to liquid to solid and, back and forth. And different states of matter for the same material have different heat capacities. This is something that a lot of people, incorrectly answer problems based on. So it's really important to understand. So you can see here that ice has a specific heat capacity of 2090 joules per kilogram Kelvin, whereas liquid water is almost double that. So 4,190. Liquid water has an unusually high heat capacity. Yet another of water's weird properties. And then steam has like around 1,900 joules per kilogram Kelvin, but steam's heat capacity is highly temperature dependent. And in fact, all heat capacities are slightly temperature dependent, but you usually only see that when you get down near absolute zero. So near absolute zero, materials will have their heat capacity dramatically decrease. And theoretically, if you could go to absolute zero for metals, the heat capacity would actually just be zero. So sometimes this is important, but not very often for this course. Anyways, but for the most part, you can just take, for a given state of matter and a given material, you can take the heat capacity as a constant, and you don't need to worry about any changes in it. Just know that if you're doing something really carefully in the future, or if you're working with gases out to very high temperature, you might have to, look some more into this idea that heat capacities can slightly change. Okay, and then I really love this picture on the left here. I want to dive into that a bit, which basically just shows what happens as you add heat to this system. I kind of hate how they have I would prefer if this graph were flipped. I think Q should be the x-axis, but they didn't ask me. But so let's imagine that we're going up here. We have a fire under our object, under our ice, let's say, and we keep adding energy to the system. What happens to the temperature? Well, at first, ice has some heat capacity, 2090 joules per kilogram Kelvin. So at first, the ice heats up, right? It starts off very cold, and then it starts to heat up. It stays ice, but it gets warmer and warmer. At a certain point, the ice stops changing temperature. And we know what temperature this happens at, right? It's 0 degrees Celsius, the freezing point of water. And so during that melting process, as we add more heat, the temperature doesn't change. And this is really critical for a lot of, biological and chemical processes. For example, when we, well, we'll get into them more later because there's a whole section on heat exchange, but you can imagine sweating involves a phase transition that, moves heat in a complex way that's not changing the temperature, at least of the material. Okay, and then once we've added enough heat to melt all of the ice, we start again on our linear, this is heating water all the way from very, very cold water, 0 degrees Celsius, all the way up to its boiling point at 100 degrees Celsius. And so for that portion of the graph, we would use water's heat capacity. You can see how, right, this is like our slope in this plot. And, delta T is our X and Q is our Y. So it's a linear relation again. But once we get to 100 degrees Celsius, we have to input a bunch of energy just to change the type of matter we're dealing with, to change the state. And so that's the process of boiling. And, this is a really useful idea when you're cooking to be aware of, is that whenever water is present in something that's being cooked, its temperature, the maximum temperature that it can have is 100 degrees Celsius. Okay, so, the water could be just simmering, in which case it has a lower temperature. But even if it's a raging boil, the water itself and anything inside of it can only be at 100 degrees Celsius. If it were hotter, it would have already boiled. Okay, and this is really useful if you have a rice cooker at home, then you'll know that they somehow magically stop cooking when they get to, the perfect doneness for the rice. And this takes into account the idea that the temperature while something is boiling doesn't change. So the rice cooker has a little mechanism that's actually brilliant. It involves magnets, so I won't get too much into it today since that's 3C material. But while the rice is cooking, the temperature will be 100 degrees Celsius because there's water, it's boiling, turning into steam. But once it's done cooking, enough of the water has left the system that its temperature can now start to rise again. Okay. And so once the little sensor detects that the temperature is a little bit higher than 100 degrees Celsius, it knows the rice is done cooking. It's all the water you've added has boiled off, and we can start, looking at the gas stage now. The temperature can get higher. Or, if you remove all the water, then you're starting to think about the temperature of the remaining material, which is usually a solid that could get substantially higher before it would start to melt. Now, there are a few things that get in the way of these transitions. The number one thing for normal materials is combustion. Okay, so we live surrounded by oxygen, which is sneaky, right? So sometimes you'll think you're going to melt something, but the oxygen will start reacting with it and it'll actually burn. But if you were out in space, and your object wasn't an oxidizer, then you could just melt it, even things that you wouldn't normally think of melting. Okay, so any questions on, we're going to dig in a little bit more into specific heat and into these phase transitions, but any questions at the moment on any of these things? Okay. So yeah, we've got the equation here for you in a little bit nicer form. And so now we can go ahead and try out an example. And so, again, a nice medical example, and we'll talk some more about how much energy the human body generates in its normal activities. And if you're in a project group doing the thermoregulation project, you'll get a lot more experience with these ideas. But we have a 70 kilogram student, so we know the mass. That's a good start. They catch the flu. Their body temperature goes from 37 degrees Celsius to 39 degrees Celsius. So that delta T is 2. We could say 2 Kelvin is our delta T. How much energy is required to raise the body's temperature? So we want to find how much energy is required, and based on that temperature change, we have almost everything. It's almost just a plug and chug problem, but we need the heat capacity of the body, which luckily was on this table. And you can see it's a little bit lower than that for water. So the body is, mostly water, but it has some solid components that have a lower heat capacity. And so I forgot to remember the value. It's 3,400. And that's joules per kilogram Kelvin. All of our units are in the right range, so we can just plug in here. I'm getting like 0.48 megajoules. So a pretty large amount of energy in terms of joules. And this is where we get an introduction to the idea that human bodies are dealing with crazy amounts of energy. I mean, the joule is kind of a small unit in general. The joule is just, basically the amount of energy it takes to lift an apple, like off a desk above your head. That's about a joule. But, human biological processes, since we're a large, massive object with a high heat capacity, any change in our temperature requires an extraordinary amount of energy. And so, the body expends a lot of energy to give you a fever. And this is why in a lot of conditions, it's good to let the fever continue, because it's serving an important process. Part of which actually we've already learned about, which is that viscosity decreases as temperature increases. So by increasing your body temperature, your white blood cells can move more quickly because of the lower viscosity of blood. So that's one of the many reasons that temperature helps your immune system, fight off some bacterial or viral threat. But anyways, so quite a bit of energy. We'll talk some more about how calories are another unit of energy, and we can convert them back and forth with joules. So we could figure out how many, snacks we would need to eat in order to generate this much energy. But we should move on to the next topic here, which is phase changes. So like I was saying, materials, we all have a lot of experience with this in our daily life. Materials can undergo these very dramatic changes. I know it's like something you learn about in elementary school, and maybe now it seems kind of silly, but from an atomic and molecular level, the change that you get during one of these, going from solid to liquid or liquid to gas, it's really extraordinary that such a thing can occur, and that it's reversible. So you can, an important feature of any phase change is that it has to be reversible. So you can freeze your water, but then you can melt it again later. So these molecular structures are really resilient to such complex changes. And for this class, we'll be focusing on solid, liquid, gas, but there are lots of other types of things, types of phenomena that you can interpret as phases. So for example, magnetism. If you have a magnet, you can interpret that as a different phase of matter. So, magnet's typically solid, but we would say that because it has this new attribute, magnetism, which is a dramatic change from what it had previously, no magnetism, that constitutes a different phase or a different state of matter. So there are, people talk about 3 states of matter or 4 states of matter. If you ask a physicist, they'll tell you that there are like an infinity of states of matter, depending on what you want to define in a given instance as a state of matter. So we usually just talk about the main 3, since those are the most common by far and the most general. But I'll give you at least one more example in a couple of slides of one that's relevant to biology. So anyways, so we saw what happens with heat for something changing temperature. So if you're in the liquid state, for example, you'll have some heat capacity, your object has some mass, then a given change in temperature relates to some change in heat. But as we saw in the diagram, these phase changes require heat, but they don't change the temperature. And so we have these much simpler equations where, for example, the heat involved for freezing is just the mass of the system times some constant of the material. So you can call it the, L freezing. The technical name is the latent heat of fusion. And thermodynamics, you don't need to know this, but in thermodynamics, a latent heat is one that doesn't change the temperature. So there you go. When you freeze ice, you turn it from a liquid to a solid. You're, in that case, taking away energy if you're freezing it. So in that case, Q would be negative for that system. And you're changing the energy, you're taking away some set amount of energy that depends on the amount of mass you have and the material. So for water, it'll just be some number for LF. So you'll just have to look it up in a table, or it'll be given to you in a problem. There's no nice way to calculate the LFs or to calculate the Cs, the specific heat capacities, because it's a very complex process that depends a lot on the crystal structures, not just on the molecules themselves. So it depends on how those molecules form, the solid, which is very tricky to model. So anyways, the hardest part about these phase change formulas is to remember this plus or minus sign, and that's something you have to do yourself. And basically the way that it works is if you're going from a more energetic state to a less energetic state, so from a gas to a liquid or from a liquid to a solid, then you have to have heat leaving the system, right? In order to form ice, the heat from the water has to be pulled out of it into the freezer where it's then dissipated. And so if heat is leaving a system, we need a minus sign in our formulas. Whereas if we're doing the opposite, if we're melting ice going from solid to liquid, or if we're boiling water going from liquid to gas, we're adding energy to the system. So we need a positive sign for the equation. Okay. Now we're gonna, in a few slides and in your discussion, put all of these tools together and do what are known as calorimetry problems, where we look at sort of having some systems that are connected, touching each other, basically, that are able to exchange energy, and we'll want to know what happens to them. So does something melt? Does it freeze? Does it just change temperature? And so in those situations, it'll be very important that we get the plus or minus signs right on these formulas. At the end of the day, though, you just have to remember, if you're heating something up, if you're giving it energy, that's positive Q. If you're taking its energy away, cooling it off, that's minus Q. That's what it comes down to. Any questions on phase changes? Oh, and I just added this fun picture to remind you that, even rocks, materials, you don't usually think about changing phase. Their liquid phase is incredibly important for the planet and plate tectonics and such things. Okay, so here are some sample values. If you look up tables online, they'll look very similar to this. This is the one from the book. But as you can see, different materials. So we'll look at water first, since that one will feel more familiar. So there's some temperature for, and this is at 1 atmosphere of pressure. That's very important. We'll talk more about that. So at a given pressure, usually if you're looking up these tables, they'll be given for atmospheric pressure, because that's the one we care about. There'll be some temperature where your substance is in equilibrium between solid state and liquid state, right? So at 0 degrees Celsius, water, you can have icy water. It can be a combination of the two states as it's transitioning one way or the other. You'll have some temperature where that transition takes place, and then some constant, your latent heat of fusion, that tells you how much energy that process takes. You can see water, again, has a very high latent heat of fusion. It's takes a lot of energy to freeze water, and that's because you're forming all of these bonds. So you have a lot of energy associated with that. And then again, we have some transition temperature where there's an equilibrium between liquid and gaseous states, and that has some energy associated with it. And yet again, water has, about 10 times more energy associated with its transition than most materials. And that's, a consequence of the fact that it's a polar molecule and that we're having to break those bonds in the liquid in order to form the gas. But you can see, there are all these other materials here. So mercury doesn't become a solid until -39 degrees Celsius. And it doesn't become a gas until 357 degrees Celsius. So for most normal temperatures, mercury is going to be a liquid. And in contrast, we can look at acetic acid that has a higher melting point. So it's easier to turn it into a solid, and there's less energy associated with that. And then it has a higher boiling point, again, with less energy relative to water associated with that. And acetic acid is really just a solution. So you can see that by adding solute to something, you not only change its chemical properties, but you also change these material properties, because you're disrupting the bonds. If you add a solute to water, typically what'll happen is you'll lower these latent heat of fusion and vaporization, because you're getting in the way of those strong hydrogen bonds between the water molecules. Okay, I think I was going to add an example there, but I'll leave it to your discussion sections to give you one. So I mentioned the fact that the pressure is 1 atmosphere for that last diagram. If you want to add all of the pressures onto the same picture, that's where we get these state diagrams, or they have a few different names, but in physics we call them state diagrams. And the x-axis here is temperature, the y-axis is pressure. So you can see, I really wish I had some more colors here, that this line, this horizontal line, tells you what water will do on the surface of the earth, basically. So if you're at a temperature of 0 degrees, then the water freezes. So if 0 and below, it's a solid. So this part is if you keep decreasing the temperature, you get colder and colder ice. If it's in this range, it's liquid. And then if you increase the temperature beyond that, it'll become a gas. And of course, if you kept going, eventually you would get a plasma or something like that. But the nice thing about this chart is that it shows you, not just at that one pressure, but at every pressure. It's a two-dimensional relationship. And so, we could ask ourselves way up here, and maybe this is a pressure you would find somewhere, reasonably deep in the ocean. 218 atmospheres, totally achievable under Earth's oceans. So in that case, water can get much hotter and remain liquid. And in fact, we observe this in undersea trenches. If you go deep underwater, then the marine life there has to evolve some special features, some special biological and chemical reactions, so that it can survive in significantly hotter water temperatures, 2 to 3 times hotter under those high pressures. Similarly, we can go, you can imagine going to a slightly lower pressure, and that would be like going to a higher altitude on Earth's surface. So if you go up to, Colorado, Denver or something, then you have, maybe a 10% reduction in atmospheric pressure just from that. And you'll see that water transitions from a liquid to a gas at a lower temperature in those cases. And so what that means is that you have to cook your food for a little bit longer because that boiling point of water isn't quite so hot. So it's a little bit lower, and you're, more slowly adding thermal energy to whatever you're trying to cook. So that's why there'll be different cooking directions for different altitudes on lots of packaging. And then, the most critical thing on this diagram is what we call the triple point. And so at some very special pressure and temperature, materials will have all 3 states of matter occur in equilibrium at the same time. So for water, it's at a very, very low pressure. So you would have to, you can do this in a lab pretty easily, but you would have to have a vacuum pump like we had last week. And you have to cool it to very close to freezing, and you'll be able to achieve steam and ice and liquid water all at the same time in the same container, and it's in equilibrium. And then it's worth mentioning this area, which is where you get sublimation and deposition. So sublimation is where you go straight from a solid to a gas, and deposition is where you go straight from a gas to a solid. Now, even at other pressures, this will happen very slowly. So if you leave ice in your freezer, over time it'll vanish. Partially that's due to the fact that modern freezers have a defrost cycle, so it's hard to attribute all of that to sublimation, but some part of that would be due to sublimation. If you're working with a lab freezer that doesn't ever have a defrost cycle, you'll still notice that ice slowly disappears, and that's happening through sublimation. But for some materials, notably carbon dioxide, they have sublimation occur at room temperature. So if you, get some dry ice, which is frozen carbon dioxide, the reason it's called dry ice is that it doesn't transition to a liquid. It sublimates directly into carbon dioxide gas. And most fire extinguishers actually use, I don't know about most these days, a lot of them are chemical foams, but a lot of fire extinguishers use dry ice for this property because the carbon dioxide, pushes away the oxygen and stops non-oxidizing flames. It also just cools things off. So even an oxidizing flame, you'll just lower the amount of thermal energy available and maybe get it below the activation energy. So anyways, this is an example of a state diagram. Your book has a few more, but they're really critical to be able to read if you want to, in one image, see the full scope of a substance. all of its different states, how it might transition between them, and when those transitions would be observable, under what conditions. Okay, so we're about halfway through class, and this has been a bit of a monologue for a while. So I want to take a break, maybe 5 minutes, and let you stretch and talk, and you can see Charm if you'd like, I guess. But yeah. So this like it's looking for food.
Yes, I was curious, is it possible if I could switch discussion section?
So
I wasn't sure what that I was but just like as much so we all it was full and so nice to go to the other different a little bit. It's like, are we playing now? Okay, so we can go ahead and jump back into it with an example problem. Everybody's favorite thing, I'm sure. So this is a great example, biologically speaking, of where a phase change has a significant impact, which is, in humans, sweating. Most animals don't sweat, but they still use the water liquid vapor transition to cool down through the respiratory system, right? So dogs like Charm pant to stay cool, but even animals that don't like pant, still when they breathe out the moist air, they take an advantage of the fact that the liquid is transitioning to a gas to cool off, because that can suck up some energy without requiring a change in temperature. Okay, so the human body produces 30 grams, some mass of perspiration per minute, which we can think of as a rate of 2 liters per hour in terms of volume during vigorous exercise. What is the rate of heat loss by evaporation for an athlete who is perspiring at this rate? Okay, so we have our formula. Q is, and we're transitioning from a liquid to a gas. So for the water itself, we have a positive change, right? The water is gaining energy as it turns into a gas. And so the body will be losing energy in the same amount of time. Okay, and they tell us the mass, so 0.03 kilograms. And then the latent heat of vaporization for water, we had back here as 22.6 times 10 to the 5th. And so we get an amount of heat, amount of energy, 7.3 times 10 to the 4th joules. So 73,000 joules. But they ask us for the rate that we're perspiring at. And so, you'll see this written as dq dt, but if you don't know calculus, you don't need to worry about the derivative here. Just remember, it's very similar to velocity. It's how much energy are we emitting or gaining over some amount of time. So we don't actually, you won't be expected to take derivatives in the class, but it's good to occasionally see the notation since it's so common even in our textbook. And so for this, basically, we can just think of this as a change in heat over a change in time. And so we had 7.3 times 10 to the 4th joules every 60 seconds, right? That was how much, 30 grams per minute of evaporative cooling. And so if we divide these things, we get 1200 watts, which is really significant. So that's, a toaster, average toaster is around 1100 watts. So that's like our body able to take all the energy from a toaster and dissipate it via evaporation, right? As the water changes from a liquid to a gas, it needs energy to do that. Where does it get the energy? By changing the temperature of the material of our body, right? Via the MCAT equation. Okay, yes?
So why is Q positive?
So I should be careful here about what I mean by the plus and minus signs. So the Q is positive here because we're going from a liquid to a gas. So we're going from a less energetic state to a more energetic state. So we have to give energy to the system. What's the system in that case? It's the water, it's the sweat. So this is for the sweat. Now, technically this dq dt, I write it as positive here. That's the amount of energy per time that the sweat is gaining. Okay, if I wanted the dq dt for the person, it would be the opposite, right? Whatever energy the sweat gains, where does it get it? It gets it from the person's body. So this would be negative 1200 watts. This is dq dt of the sweat. It's positive. So very good question. And this is our first example actually of calorimetry, which is a fancy word for basically saying that if you just have, X number of objects, that the energy can only be passed between them. And so if we use these thermodynamics equations to determine the amount of energy that some change requires, that energy has to come from somewhere. And so it comes from one of the other things in the system, one of the other things touching that object typically. So we'll get some more examples with that. But these calorimetry problems, it's important you're able to do them because they're really relevant to human health. Heat stroke and hyperthermia and all these things are based on principles from calorimetry, but the problems tend to be very long. So you'll have some in your homework, of course, and your discussion section will also on Tuesday do at least 1 or 2 calorimetry problems. Okay, but you may have, I don't know, have people seen these problems in chemistry before? Yes, okay, so potentially some people have already seen them. Okay, so then I promised to give you another example of a phase change, and I think this is a fun one. So some proteins, so proteins generally can be folded or unfolded in the body. So you see this occurring like when you scramble eggs, right? That's the process of a protein changing its state. But so that state change though wouldn't be considered a different phase of matter because it's not reversible. So when you scramble an egg, well, there are some labs that are trying to show that you can unscramble eggs, but it's not an easy thing to do. So effectively, it's irreversible. But some protein folding transitions actually are reversible. And so we can think of them as a phase change. And what you see is that, so this y-axis is a fraction folded, but you could also say that this is some energy Q. And so as we add energy to the system, our temperature changes at first, but then at a certain point, it doesn't change very much. And that's in our transition from a folded up protein to an unfolded protein. So increasing the disorder of the system. And then once the protein is all unfolded, it starts to be able to change its temperature again as heat is added. So it's a fun example of a biological process where you see a phase change that's not a solid, liquid, or gas phase change. It's due to the amount of protein in some region that's folded or unfolded. So anyways, you don't actually have to do any calculations with that at the moment, but I thought I'd mention it. Okay, so I know I've been hyping them up a bit, and I'm not going to read through all of this because reading slides is really terrible. But I wanted to give you this so when you review the lecture slides, you'll have it very present in your mind, but this is also in the book. So the idea behind calorimetry is that, in its simplest example is you have 2 things in a box, an insulating box. And the only way that they can gain or lose heat is by transferring it to the other object. So if one object gains energy, the other has to lose it, and vice versa. It's a zero-sum game inside this box. And so, what we can do is we can just start with this idea of energy conservation, that the heat for object 1 plus the heat for object 2 is just 0. Remember that heat is already telling you a change in energy, so you don't have to talk about changes in heat. We just need to talk about the amount of heat, which is the amount of energy being gained or lost. And so what we'll do, as you'll see, is, let's say that these 2 states are both, there's our system 1 and system 2 in the image are both liquids that aren't near their boiling or freezing point. So in that case, we could just use these MCAT equations. We would just say that, for this system, it has some temperature T2. For this system, it has some temperature T1. And so we can just say that this system has some Q1, which is MC delta T, and this system has some Q2, which is MC delta T. And we can say that the any transition between these 2 will be balanced by gain or loss in the other one. The story gets more complicated when we have different states of matter either present or available to us in the transition. So for example, a lot of the problems we'll give you will just be one element or one molecule. So you might have some, 2 clumps of liquid water, one at 10 degrees Celsius, one at 20 degrees Celsius. If they're the same mass, when you mix them, you'll get a bigger clump at 15 degrees Celsius, right? One will have cooled off, one will have heated up until they're in equilibrium. But you could just as well ask, what if I have some ice and some water? And so now there are 2 possibilities, or really 3 possibilities. So one possibility is you have more ice such that the water freezes, right? If the ice were started off colder than 0, then you could get everything to turn into ice and it would be at some temperature. Another possibility is that the ice melts and you end up with all water at some temperature between 0 and 100 degrees Celsius. And then lastly, you could just somehow get right on the money and have some amount of water and some amount of ice, which would tell you the system is at exactly 0 degrees Celsius. That's the only temperature at 1 atmosphere of pressure where those two can be in equilibrium. Okay, and so like I said, you'll get plenty of practice with this, but it's good to have some idea, abstract idea of what we're going to be doing, so that when you get into all these annoying algebraic steps, you don't get lost, forest for the trees and all that. Okay, so yeah, practice problem and discussion. So very similar to the phase change calorimetry, we also use calorimetry in chemistry to talk about how much heat some reaction is either emitting or absorbing, right? Negative or positive heat. And so typically what will happen in that sort of situation is that you'll have a bath of water around some reaction vessel, and the reaction vessel will be pretty small. So we can primarily think of any temperature change as being in the water, but if you're being precise, you would include every element in thermal contact. And then it's surrounded by some insulation. Okay, and what we do is you can imagine this is like something that you're able to burn. So we burn our reactants, they emit some energy, and we notice some change in the heat of the system, or in the energy of the system based on the temperature. So if the water is not boiling, then we can just use the Q equals MC delta T. So the water will heat up by some amount, has some heat capacity and some mass. And then in order to get the molar heat of combustion for that reaction, we just have to say, well, if the water heated up by some amount, it gained energy, then the system, the reactants, had to exert energy, had to exude it. And so that would be an exothermic reaction, which has a negative heat of combustion. And we would divide by the number of moles of reactants, since chemists love to do everything in a sort of an amount per mole, right? So at the end of the day, this would give us a joules per mole Kelvin, where a negative value would be an exothermic reaction. And so we won't be doing many calorimetry problems with reactants in this class, because we'll leave that to your chemistry teachers. But it's kind of good to see, and we might do one or two just to give you a taste of it, that it's the same process as we have when we're just dealing with different objects at different temperatures or different states. Okay, so moving on now to heat transfer. So we've already talked a little bit about the primary and most efficient form of heat transfer in almost all applications, which is conduction. So conduction is just what occurs when you have two things in contact with each other. Typically, it's the primary form of heat transfer for solids, so solid to solid. So for example, when I touch this wall, I'm conducting my heat, since I'm hotter than the wall, from my hand into the material, the paint and plaster and everything else. So that's one of the methods. But for fluids, it turns out conduction is very inefficient. So conduction in fluids are really bad at transmitting heat, and that's we'll talk about why in a second. But as a result, they have another primary form of heat transfer, which is convection. And convection is the idea that when you heat up substances, you create fluid flows, typically because when you heat a substance, its density will change, it'll decrease generally. And so you get, some less dense region and some more dense region that will try to move into each other to create some new equilibrium. And that will transmit heat in the process. That's convection. And then radiation, which again, we'll dig into the details of, is where you heat up an object and it emits energy in the form of light. So when you have a fire, that light that's being emitted
is telling you that it's hot. Or when you have a pot on the stove and you let it get, scorching hot, maybe red hot. But it turns out that radiation is always emitted no matter what temperature something's at. It's just that the wavelength of the radiation changes. So humans, even though we look dark to each other because our eyes don't see in the infrared, are emitting tons of radiation all the time, just infrared radiation. And if you're a snake of certain species, you can see that energy and you would see humans as glowing lights, ready to hide from them or bite them if you have to. Okay, so the first thing that we'll dig into the details of then is conduction, or sorry, conduction. There we go. Let me write this down so I don't confuse myself. And so conduction has a very straightforward, yet again, linear formula. So that's why we're gonna, want you to learn it, which basically just says that the rate of heat transfer, so how much energy per time, how many watts of energy do you transfer, is proportional to the difference in temperature of the two systems. And what's the proportionality constant? Well, it's some number K that depends on the material times the area of the contact, right? So if I have a cold bench that I'm going to sit on, maybe I just barely sit on the edge of it, that's minimizing the area of contact. Whereas if I put my whole butt on it, then I've increased dramatically the area of contact and I'll have a much higher rate of heat transfer via conduction. And then I'm going to divide by the length. So this is telling you that, if you have the way that we do these conduction problems is we think about them in terms of a hot region, a cold region, and some insulating layer. And so the insulating layer is the thing that we use for our K, our heat transfer coefficient, and it's the thing that we consider when we're talking about how thick it is. So the thicker the insulation, the bigger L is, and the lower the rate of heat transfer via conduction. Okay, and so what I wanted to point out here are a few of the values for the heat transfer coefficient. So you can see they're in units of watts per meter Kelvin. Yet again, we have a delta T in this equation, so we can use Celsius or Kelvin here, it's equivalent. And you'll notice that diamond has a really surprisingly high, actually the highest measured other than carbon nanotubes or random weird stuff. The highest heat transfer coefficient of any material. And this is actually one of the ways that you can test if a diamond is real. You'll see those little probes. I get a lot of YouTube video recommendations for them these days. And one of the ways that those can be designed is by having one hot probe and then one temperature detector called a thermocouple. And by measuring how long it takes for that diamond to transfer that heat, you can tell if it's real. If it does it very quickly within a second or two, then that's likely a real diamond. But some materials can fool these detectors. So they also make refractive diamond testers that we'll cover later in the course, because we'll also be talking about refraction in this class. So anyways, metals are also very high, but not quite as high as diamond. So a few hundred is a typical value for a metal in terms of conductive heat transfer. And then things like, muscle and fat, so biological tissues, are very good thermal insulators. And then you'll notice we have air on here. Now this is a little confusing because, so air, you can see this is a very low value. It doesn't transmit energy well via conduction. But if you're in this room, you'll definitely feel yourself cooling off. I know I have since I walked in. And so that is via convection. Okay, the air is able to be hot in one region, change its density, move away, and be replaced by new air. And this process is really, really efficient because what you're doing is you're increasing that A, basically. So the air in contact with your body can only transmit energy via conduction, and it has a low conductive heat transfer coefficient, so it does that slowly. But by allowing the air to flow away from your body as it heats up, you're making the area of contact, the effective amount of air that you're touching, super big.
right? You're in contact with tons of air. And so even though K is small, A is very big in that case, so you cool off. And that's what convection is. Now, the very low thermal heat transfer rate of air means that if you can trap air so that it can't move, then you'll have a very good insulator. And so that's what a lot of animals do, right? They have fur or feathers or something else. And what that's doing is it's trapping little pockets of air such that they can take advantage of the fact that it has a low conductive heat transfer without being weighed down by this convection. And so that's why styrofoam, for example, has such a low heat transfer rate, is due to the fact that it's mostly air. It's just being held still. Okay, so there's a lot of words involved in this problem, but it could have been said much more straightforwardly. But if you're sitting on a 10 degrees Celsius bench and your body is at 37 degrees Celsius, then we can get our delta T. It's just 27 Kelvin. And you're protected from the bench by a 1 centimeter thick layer of fat. So your L is 0.01 meters. That's the separation between the hot and the cold is being provided by this insulating material. And then we should go look up the K value for human fat. So it's 0.21. And that's in units of watts per meter Kelvin. And then lastly, we have some area. So the area of contact, basically the area of your butt, is roughly 0.1 square meters. And so you can see that we can just plug these things in, right? We don't have to really do much in these problems generally. We just say dq dt is Ka delta T over L, and we know all of those things. So we can plug them in. And get 57 watts. So you can see, it's a reasonable value. You'll definitely notice it if you sit on a cold bench, but it's much smaller than the amount of heat loss that you experience when sweating, for example, which can be 1,000 watts. And so, primarily that's just a result of the fact that the whole area of a human is about 2 square meters, whereas this is only thermal contact over 0.1 square meters. So, 1/20th of your area. But like I said, these heat transfer problems, generally they'll be pretty straightforward. You might have to find the change in temperature based on some rate of heat transfer. You'll just have to rearrange the equation. But just because there's a derivative symbol in here doesn't mean you actually have to take any derivatives when you're doing the problems. So I mentioned convection. In this class, we won't actually have any equations related to convection. So maybe to some people, that'll just mean you don't have to care about it too much. But I do expect you to qualitatively know that convection exists, and that if you're in contact with a fluid of a different temperature, that will be the primary method by which heat is transferred. And so the reason we won't deal with any of the equations is because they're very complicated. And if you are interested in them, that would be one of the main topics of a stellar astrophysics class, because star formation and development is highly dependent when they get really big on convective currents. So that's usually where we talk about them the most. So then we'll move right on to radiation, which is the third type of heat transfer. And so, like I said, if you look on the right word picture, you can see that when you heat up objects, they start to glow. Like, primarily we see this in metals since they don't burn very easily. And so you can see that the color that it's glowing at depends on the temperature of the object. So a lower temperature means that you'll have a glow that's more red, whereas a higher temperature makes it more orange, yellow, all the way up to white.
And so what's happening here is that we have the rainbow from red to blue. And, if we kept going this way, we would hit the infrared and the radio and such things. And if we kept going this way, we would hit the ultraviolet and higher, X-rays and gamma rays. And it turns out, this is a spectrum, the electromagnetic spectrum, and whatever temperature you're at corresponds to some, primary color, primary output at a certain point on the electromagnetic spectrum. And so for humans, we're somewhere over here out in the infrared. That's where we emit our radiation because we're at a temperature, our human body temperature, 37°C, that is described by emission in that spectrum. So it doesn't matter what your object is made of. Any object that was at the same temperature as our body would have the same colors and types of light emitted. So it's just a property of the temperature of the object, not of the temperature difference. So this is an example where we will use kelvins. Whereas, once you start heating up a metal, eventually you'll get them into this red hot region here. Once they're in this blue hot region, we don't actually see that because of how our eyes experience color. We just kind of see that as having all the colors. And so that's why we get white. So this white hot area is where we've now transitioned such that the peak of the emission is in the green to blue sort of wavelength. But you always have to be aware of our limitations in our senses, that, our senses have more sensitivity to some colors or to some sounds, and this can cause some problems in your intuition. And so again, we see that on the left, this infrared emission, confusingly, the blue regions here are like longer wavelength infrared, and the red regions are shorter wavelength infrared, closer to red light. But they're trying to convey temperature, which is what, usually we think of blue as a cool temperature. And so we use satellites to measure the infrared radiation being emitted by all of the Earth at all different moments in time. We have enough satellites, we can see it all at once. And this is invaluable data for weather forecasting. So, by measuring the infrared energy emitted, we can pin down the temperature of the air at each region. And that allows us to predict how the weather is going to change over time in different areas. And so we do have a formula for the radiative heat transfer. Even though it's a little more complex, it's not too much worse. So instead of just having a delta T, here we have a T to the 4th power. Okay. So what that tells you is that the higher the temperature of an object, it's going to emit significantly more energy via radiation. So where do you see radiation being the primary form of heat transfer? In very hot objects. Okay. And that has to be hot relative to their surroundings, because it turns out this same equation describes the energy emitted via radiation and the energy absorbed via radiation. Okay. And then I should just mention, so this A is just the area of the object. So if an object has more surface area, it'll emit more radiation. This sigma is just a constant of nature. It's the Boltzmann constant, Planck-Boltzmann constant. And then this E is called the emissivity. Write that out. And this is a property of the material. Basically, it's describing how good is it at emitting energy via radiation. And so if something has an emissivity of 1, it's really good. So good radiator. And if it has an emissivity of 0, it's a really bad radiator. And that's the range of values. So it's between 0 and 1. If you're not told what it is, just take it to be 1. It's usually a good estimate. So sort of the typical value is very close to 1 for this emissivity. And then we're basically out of time for today, but I just wanted to quickly tell you that this graph here, won the Nobel Prize and was the product of like 50 years of research by hundreds of physicists. So nothing to scoff at in the early 20th century. And it was one of the ways that quantum mechanics was first identified as being necessary. And basically it's showing you how much of each type of light do you get from a given object based on its temperature. So when something is 3000 Kelvin, you can see that the primary type of light you get is the red to infrared. And this plot tells you how much of each type of light you'll get. And basically by integrating this, you can get the radiative heat transfer equation. So good to be aware of, but you won't have to deal with those plots much other than knowing that the hotter an object is, the more its light that's being emitted changes into the higher frequency. So the whiter light to UV. Anyways, that's it for today. Like I said, no office hours right now. I'll send an announcement about when the makeup ones are. We'll definitely have them on Wednesday after class. And good luck with the homework.